Well, so hello everybody. Thank you for being here. My name is Alejandra and I come to speak to you about the implementation of contrail avoidance in commercial flight planning. As Manuel said, I was supposed to come here last week, but alas, I'm here today, so I hope you like the little mix of topics. I couldn't start my industrial PhD topic without talking about my sponsor, FlightKeys. FlightKeys is a flight planning software company. We are based in Vienna and we operate with airlines all around the world. We sell 3 core products: FlightKeys for ID, our flight dispatching tool, SpaceKeys for rain prediction, and Loretta, which is an EFB tool for pilots in flight. Since I guess outside of 3 people that I see, not everybody here knows what contrails are, I'm gonna make a very, very short introduction in case you didn't pay attention last week. So contrails are those thin white lines that we see in the sky on a clear day. Madrid is full of them. You just need to look out the window. They form when the cool ambient air condenses on the warm soot particles liberated by the engine, and they freeze, forming the cloud behind the aircraft. Contrails, like any natural cloud, have the ability to alter the energy balance of the Earth. On the one hand, they can reflect part of the insular radiation back to space, but they can also trap part of the outgoing infrared radiation within the surface, creating both a cooling and a warming effect. However, in general, it is believed that contrail as a whole have a warming effect on the climate, and this is why us as an industry are trying to avoid it. So how can we as an industry achieve contrail mitigation? Well, there's 3 techniques. Sustainable aviation fuels, which basically could alter the properties of the contrails. New engine technology, the better the engine, the less soot it liberates. And last but not least, intelligent flight operations. Since FlightKeys does not do engines nor SAF, as the best of my understanding, we're going to talk about the last one. And how do we implement contrail avoidance from a practical perspective? Well, there's 2 stages: the pre-tactical strategic avoidance and the tactical avoidance. Pre-tactical avoidance usually happens between 3 and 6 hours before departure. A dispatcher is sitting with its computer and checks the flights of the day, and they get a list of which flights are predicted to form contrail avoidance, and then the dispatcher can choose to plan a route that avoids these contrail probability areas. This flight plan then gets filed, and ATC has hopefully, the decision to approve it, and then this flight plan goes directly to the pilot, where with the latest weather forecast, the pilot will be responsible to make last-minute decisions to avoid contrail areas with the latest weather forecast. So this year, the biggest thing that I accomplished for my PhD, which I published my first journal paper, where we analyzed around 85,000 flights of one of our customers, American Airlines, throughout 2 weeks in summer, 2 weeks in winter. And the goal of this paper was to check the operational risks of performing contrail avoidance in a large scale for an airline. We considered 3 rerouting strategies. The first one, to reroute every single flight that generated a warming contrail. The second one, to reroute only the 2% of flights that generated warming, like the most warming contrails. And last but not least, to perform a decision based on cost. So which airlines could you invest less money while having the biggest reduction in energy forcing proportionally? So something that I didn't mention, again, depending on the model, there's different metrics, but for the model that we use here, which is called the COSIP model, we use the metric of energy forcing, which is measured in joules. It's like any energy measurement system. And what were the results that we got? Well, we saw that for a high reduction in the total warming of the flights, the increase in fuel and cost was actually very low, less than 1%, which is something that airlines were very scared about, because the general prediction at the beginning of this whole conversation some years ago was that the increase in fuel was going to be of around 5%. And don't get me wrong, we are increasing fuel, but the proportion is very low, between 0.02 and 0.11. And a question that we usually get is, well, but if we are burning more fuel to avoid contrails, doesn't this mean that we're going to generate more warming after all? So what we did is that we transformed the warming of a contrail to CO2 equivalent through different ways. And then we sum up the CO2 equivalent to the total CO2 liberated through the fuel burn. And then we can compare the original scenario versus the rerouted scenario. And we can see that for any of these 3 cases, the total warming of the total set of flights gets reduced despite increasing the fuel burn. So you say, this is great. And what do airlines think? Well, airlines have very mixed feelings about the whole thing. And we can't talk about the mixed feelings of airlines without giving a small introduction to the uncertainties and risks of this entire operation. So when we talk about the uncertainties of contrails, we are talking about the uncertainty of short-term predictions. This comes through the weather uncertainty, the model uncertainty, and of course, the everlasting question of we plan a route, can we actually fly it the day of the flight? And these are all very fair questions. But something that we always tell the airline is, well, this is not different what you do anyway for turbulence or any other weather-related avoidance. You do the best that you can pre-tactically during the flight planning phase, and then during flight, pilots are the one who are going to decide which reroutes to perform with the latest weather forecast. And they say, okay, yeah, whatever. But turbulence is for safety, whatever, whatever. So what are the numbers? How much certainty do we actually have on contrails? So specifically for the model that we're using, the COSIP model, this year a Google study came out saying that approximately 1/3 of contrails that are predicted using this COSIP model can be detected using satellite imagery. And airlines say, well, but 1/3 is very, very little, and we're also increasing fuel burn. So is it still worth it? So now we go back to the same table I showed you before. As for the operational risks, they remain the same. We are going to reroute the same amount of flights and waste, or willing to waste the same amount of fuel and cost. This is like when you go to a casino and you say, tonight I'm spending 100 euros no matter the return that I get. What happens if we only have a 33.3% chance of actually getting it wrong and a 77.37% chance of getting it right? So we see that the reduction, even though way less than in the original case, still happens. Instead of 69%, 70%, we are talking around 20%. And the total warming, again, despite the increase of CO2, still gets reduced of around 6%. So this is great, right? Like this is what we tell airlines, like, hey, despite the high uncertainty, contrail avoidance could still be a solution for today to reduce the total warming of aviation without having to wait 50 years or 30 years for new SAF or engine technology. And what comes next for both the industrial PhD, but as the topic of contrail avoidance in general for the industry? Where the first thing is to implement soft restrictions. For this first simulation that I performed, I implemented contrail probability areas as no-fly zones, as any other aerospace restriction that exists, well, in the airspace. And this is not very practical, to say the least. ATC would kill me if you propose this, and I already have too many ATC people trying to kill me to increase the number. So instead, what we would do is implement contrail avoidance as another weather layer that comes the same way as a turbulence layer or any other layer. Airlines can choose which areas to avoid and which ones not, depending on their own strategy when it comes to commercial implementation. Another thing that many people don't know about the airline industry and flight planning, many people think that airlines operate for minimum fuel, but actually that's bollocks. They operate for minimum cost always, and in some cases it matches because fuel costs money, but in many other cases, not necessarily. So the way we would have to implement these soft restrictions into our system would be to set a price to a joule of energy or to ATR 20 metric or whatever metric we choose, depending on the model that we are using at the time. And then we would optimize, considering this cost for energy forcing, for example. The higher the cost, the more the optimizer will try to reroute around these areas. So for example, in this map, that again, this was already implemented, that's why we have the tick, the red areas are the most warming areas, the yellowish orange areas are less warming, they form like a spectrum. So depending on the price that you set, the operator can choose to cross the yellow areas, close the orange areas, only above the red areas, etc., etc. And last but not least, so we would perform a simulation this summer using this new cost-based avoidance system. And the goal is to fine-tune and more in-depth analysis of the cost operation of contrail avoidance with the goal of, in a year from now, a couple of years from now, for it to serve as a basis for policymakers and airlines to make informed decisions of what it really takes to perform contrail avoidance and hopefully motivate them to perform it. With this being said, if you ever buy an airline and want any contrail avoidance, advice, please contact me. Until then, it was a pleasure. Any questions, please go ahead.